Okay, great. We'll get kicked off, and then as people join, they can obviously jump in, and then obviously we're going to be starting to we'll obviously share the video afterwards. But welcome to everybody that's just joining us, and we're really excited to do like our first ever Haskell edition of the online meetup. So it should be a really great little event we've got planned up. So obviously we've got Simon, he's a functional compiler engineer, and he's going to give us his talk on roll your type, offering a brighter future. And then we've got Michael Snoyman, VP of Engineering, giving us a talk on what makes Haskell unique. So we've got some really, really exciting things coming up. If you guys have any questions, feel free to use the Q&A section down there. That way we can keep an eye on the questions that are being asked throughout the talks, and at the end each speaker will have like a chance to go back through and we'll make sure any of your questions are answered, and then again at the end you can have a little round up and anything you want to ask. We've also got our poll section. As I mentioned, this is our first Haskell edition, so going forward we want to make sure that we've got like great meetup content for you guys, and that you are seeing the topics that you'd love to hear about. So as people start joining, we'll get the speakers kicked off. So Simon, do you want to jump into your talk?
Yeah, absolutely. So the topic I'm going to talk about is row types. And give me just 1 minute to save some bandwidth. I'm going to find this button here. Perfect. Okay. So I'm going to talk about row types, which currently are in development for Haskell. However, they already exist in PureScript, which is a language which is quite similar to Haskell, but it compiles to JavaScript instead. Like one of the bigger features there is basically row types, and I'm going to talk about them a bit more. When you start programming Haskell, or this example here is probably a bit more specific for web applications, you start hitting the issue rather early that you cannot have two declarations or two fields of a record of exactly the same name. That is basically because Haskell does not have a concept of namespaces per data type. So it's all of those IDs are basically in the top level namespace, so you cannot have two functions of name ID. And if you're using the record syntax in Haskell, that's basically what you're using. Now there are a few workarounds on those. I'm like a few things like duplicate record fields, but I'm not going to talk about them. Instead, I'm going to explicitly talk about how the whole solution could look like with row types. Now, how do they look like? The same example in PureScript would basically be similarly looking, except you don't declare a new data type. Instead, you declare a type alias. And there is no error message coming out from having two of the same field name. So if you use this, we get a 3 and a 42 just as expected. There is no specific, this is nothing special, it's just works. I explicitly also added the two type annotations to verify, yes, those are the correct types. Additionally, if coming from Haskell, you see log instead of print. That's because of the JavaScript background where you have console.log instead of print. Another use case is very common with web services, where you have a whole lot of JSON. If you deal with JSON, it is very likely that you will have the same field of the same name twice. Prime example, ID. Basically, every other record will have an ID included. And this will clash sooner rather than later. Now, with the row types in PureScript, you can basically have an inline type definition and simply parse it out of that. If you take a bit of a closer look, there is in the type signature, there's an underscore there. This is basically a typo where I'm simply saying, I'm not mentioning this part of the type, go figure it out. It's an either with a bunch of, with some type for the errors, but this is not what I want to put the focus on here. Instead, I want to put the focus on that you basically have the ability to have anonymous record types and can use them to decode JSON. Now, this does look a bit like magic. It is until you understand how it works, roughly, and I want to see that I can get you all there. So let's start out by removing a bunch of syntax structure. So the first one is, you saw the type aliases, which have been declared as user and book here. And the curly braces mean those are records. Now we can disassemble this into the actual proper row type, which has the round parentheses, and put the record in front. Basically, the above is simply a syntax structure for the 2 lines at the bottom. They are exactly the same in the end. Now that we have disassembled the parts, we can take them apart and take a look at each individual part. So now I basically took out the user row and put them in its own type alias, and now we can inspect what those things actually are. So the user is quite expectedly of kind type. And apparently somebody has some sound problems. Could somebody else confirm that they are actually hearing sound? Okay, in that case.
Sorry, I'm just having a look. Nobody is everybody okay hearing the sound? Oh.
Yeah, okay, so it's fine.
Yeah?
Okay, we're basically in the kind user. This kind allows you to check what kind this is type. It's of kind type, which is basically everything. It's the standard type for things that you can actually make a value of. So it's basically the thing you know. Then we can take a look at the user row. Now, if you ask the compiler, it will say row type. This is 90% true, because currently it will say hash type, which stands for row type. But with the newer compiler coming out soon, it will then say row type, which is one thing less you have to learn, which is quite nice in my opinion. And then we can take a look, what is exactly record? This is not really a keyword. Instead, it is a type which takes a row type and then gives you an actual type. So it basically takes a definition in terms of a row type and then pass that to record, and you will get a regular type out. And whenever you have a type, you can actually make a value of it. So to assemble the whole thing, you basically have record, which is a function from row type to type, and you pass it in a row type, you get out the type. This is basically how the construction of a record works here. Any questions so far?
If you guys have any questions, feel free to use the little Q&A section down there as well, so we can keep an eye on any questions throughout the talk.
I might actually, because of the nice Q&A thing, I think I'll continue and answer questions as long as they develop.
Yeah, cool.
Now, basically, now that we have the very basics, there is a next concept, which is open rows. So you can have open row types. Let's take an error message. For example, here, I'm trying to access the label email, which does not exist. So we get a longer error message. And I also added the type string on email to get a bit of a better error message here. So the explicit part, or the interesting part about the error message, is basically saying that the type which has the 2 labels ID and name should be at least as general as something with email in them. Now we have this new syntax of pipe type variable. And now we can play with it. So we have type with email, where we have email type t, which gives us the error message that the variable t is undefined. So we add it, which works just fine. So we can then continue with it. We can then try to say we make a value of a record and tell the compiler this is of type with email, which gives us an error message which says it must be of kind type. It's basically going back to saying that you can only instantiate something that is of kind type. Now that we know we actually have to put it there, we can actually simply put a row in there and make a type of that. So we basically can combine, we have the with email, and we can combine that with user row, and we have a fully fledged type, which we can make a record for. Now, a bit more on the open row types. The syntax is, as you already saw, a pipe and then a type variable or more rows. Both works just fine. Now let's say you have two open row types. There is a special syntax. Well, it's not actually special syntax. It's simply something defined in the standard library which you can use, which is the plus operator for types. So you can add them together instead of manually applying them and inserting parentheses so everything works out correctly. You can use the plus operator and you will get back what you had initially. So this type user is exactly the same as we had before with the three labels ID, email, and name, all of type string. And those are the same type as beforehand. There is a slightly different syntax which you can also use, basically because you can say that after a pipe, you can add any kind of record types. Then you can use this as a different syntax for a record and whatever else, whatever row type you have to put in there. Now, one of the limitations is that the compiler cannot close row types for you. I did not bring an example here because this is basically one thing which I discovered while trying to do a bit of advanced type magic, but I forgot the exact situation which I encountered it. However, I can tell you that as soon as you get into that situation, you will remember this part here and then realize, oh, it actually applies for this part here. Now, this is basically the base implementation. There are Pursuit, which is basically the Google of PureScript. There's a few libraries which play with those row types. Record, Record Extra, which has a few interesting additions to records, and variants. I'm going to talk about the record library and a few examples from there. From there on, it should be somewhat straightforward to understand how Record Extra and variants work. Variants is the concept that now we have row types, which we can use to create product types, aka records. We can also use sum types to create extensible. We can use variants to create extensible sum types, which is basically you can have an extensible either with row types. You can use quite a few things with that. You could think of interpreters, error handlers, but I don't have any explicit examples for that. Instead, I want to explain how the row types work in and by themselves a bit. So the first signature you see when you open up PureScript record is this one, which is the type signature for get, which allows you to get a single element from a row type. Now I will go over those various parts of the type signature and explain how exactly they work. So the first part is symbol, and combined with sproxy, which declares a type level string. It's like a normal string, except it exists as a type and not as a value. And for the Haskell, for the people who have a bit more experience with Haskell and the proxies there, in PureScript you don't have kind polymorphism yet, so we have to use a specific proxy for each type. But basically what a symbol allows you to do is it allows you to reflect a type level string into a value level string, which basically means that if you have a certain type, you can then have a runtime value string for that. This will allow you to say which label you mean, for example, email or name. Now the next part is the workhorse, cons. There's a few type variables from there, but I will explain them explicitly so that you get an overview on the different how they work together. Currently, the type signature also has hash type instead of row type, but I found this easier to read. Now, if you go look for cons in the pursuit, you will find 3. There's one for row, there's one for row list, and there's one for symbol. I'm currently going to talk about the row one. The row list one works fairly similar. And the symbol one is so you can append or dissect type level strings. Now, how does a row con look like? Or how does it actually get applied? So now we're going to get the name from a user. Now from here on out, basically we have this type user. Then we dissect this to try to match it up because we have to take the user part, the name. We have to make that separate, and then we have to have the tail. So we basically separate into a head and a tail, which should sound familiar to people that have already worked with linked lists. You basically separate a head, you work with the head, and then you use the tail with further operations and recurse down over it. This is basically how this works. Now, one thing that is different from linked lists is that you can pick any of the rows. So you can pick, here I picked the label name, which is in the middle. You could also pick email, which is at the end, or ID, which is in the front. It's in the front for syntax purposes. But the compiler doesn't care, which is the one big thing which you currently cannot emulate with stock GHC, which is have a data structure on the type level where the compiler does not care where exactly it is. Well, you can, but the main issue then is you get exponential processing costs. Here it's linear. You can basically, the compiler does not have any issues picking, it's basically not more expensive picking email over name because to the compiler, things are unordered. Now that we have separated user tail and the head, which is basically the line at the bottom saying user is exactly the same as the line on top saying user. So one of the questions is basically why PureScript instead of Haskell itself. It's simply because this concept of row types has not been implemented like this in Haskell yet. It is a concept that is currently in process of actually being implemented. So it's basically a new feature that will come soon, TM. Okay, from there on out, we can take the little step and replace the syntax, like the curly parenthesis syntax with the round parenthesis syntax. And then continue on and actually plug this into the type class. Now we have the label, which is the name which we're using, A, which is the string. Then we have the tail, which we already separated out, and the row, which we now have, which basically says the whole row we were working with. Now we can also explain at the bottom of the cons, you have those annotations, which are so-called functional dependencies, which say that if I know label, an A and the tail, I can infer row from it. This allows you to basically go the other way around and say, here I have a tail and I want to prepend a new row. Or basically I have a row tail and I want to prepend a new row in front of it. This allows you to then infer the full row. Or the other way around, if you have the label and the row, which we have here, because we have name and the full record, so this is our row. And then we can infer from that which type we're going to get back and the new tail. This is where should also basically click together into one explicit, into why the functional dependencies are like that. Now with get with the actual get itself, we can now plug in the types again and see that the R in the signature is the full row. From the cons, the R dash is basically the tail, which is not getting used anymore in the type signature, in the actual function signature. So we can simply say we throw it away because we don't care. We only care about the head. And we have the label, which is getting passed in as name, and the A, which is a string. Now, what else is possible? We can also go for actually setting values. Here we have two cons instead of just one. This is because the current value has type A, but the one we set has type P. This does allow us to set a different type in that specific label which we used instead of keeping the same type. So we can change the actual type itself. Another thing which we can also do is merge records. I did not go into the type signatures here because most of the time you use them just like this. And you add, the compiler will tell you a few error message, what kind of constraints are missing if you need them, and then you add them in from the error messages. There's two ways how you can merge things. There might even be three, but I mostly remember those two. Merge, which is better if you know both input types, and disjoint union, which is better if you know one input type and the output type. That's simply because how the tab inference works, that makes it easier or generates better error messages. Another thing which you can do is you can rename fields. So you can change the label of a single field. How is this useful? For an example, I have here from the documentation of simple JSON, one way how you could decode a incoming JSON and change one of the field names. Often when you have to talk with JSON, it might be that some people are naming things slightly differently from different sources. It does happen, sadly. So what you can do is during the decode step, you can rename without actually having to declare a intermediate data type. You can rename a specific field to another one. This is a very small scale example, but from experience, once you start having 20 fields in your JSON types, you will be very grateful for this. It also has one interesting consequence, which is that you can combine automatic and manual derivation from JSON data types. Because if you do automatic derivation, you can only use automatic derivation if you derive all of your field decoders. And as soon as you have to change one, you have to write the whole thing out. This renaming allows you basically to change only one out without losing auto derivation on everything else. Another way how you can use the merge operation is for default values for arguments. You can, with this, you can basically say, here's my record of optional attributes, and you can pass me as many as you want. You can also pass me 0, and then it will take the defaults. So the idea here is that we merge the existing the passed in options with the default options, which we declared. And then we get everything that has been passed in replaced in the defaults, because merge, when it finds a conflict, picks the first one, the values from the first operation, or sorry, from the first record. This is how you could implement optional attributes in PureScript. Highly recommend this method because it is fairly straightforward to use and also looks nice. Now, another benefit you get from, because a record is a type which you can match on for type classes, because you have record and then you have the row type, is you can actually implement instances for record. What exists, there is an equality instance for records, semigroup for adding things together, monoids, hating algebras, which is something that's kind of, or mostly, I don't think, it probably exists somewhere in Haskell library, but the standard library has the standard Boolean operations and show naturally. So how does this look like? You can use the semigroup operator to append two records together, which will then result in the fields being added one by one, corresponding to their semigroup instance. Another one which I was talking about is the hating algebra, which allows you to use Boolean operations. Naturally, also other libraries, for example, the simple JSON I was mentioning, can allow you to define your own instance or defines an instance for record, which is how it works basically. And because of that, you don't have to specifically derive, like in Haskell, where you have to, for example, derive JSON instances. You don't have to do that anymore for records because you can already declare one which is generally applicable for any record. On the other hand, that means if you want to decode your thing a bit differently, you have to use new types to attach more data on top. Now that we have roughly seen how the whole thing looks like in PureScript, there's a few things on how it would actually look like in Haskell once it's implemented. One of the things is basically on how you actually iterate over the types is done via type classes in PureScript, because PureScript does not have type families, which are basically type level matching operations. Another thing, one thing which I have to explicitly say is that the GHC or Haskell implementation for row types will not have a backend for it. So what GHC will implement is simply the row type part, not the record part. The record part is basically up to user implementation, and I see a few libraries popping up which use those row types in GHC to implement their own backend. Now, one of the things is that Haskell doesn't have a JIT, so just a time compiler. Why is this relevant? Specifically, if you have an open row, that means you do not know where exactly in your data type set data is. With existing records, you can simply paste them one after another and then have a pointer to each one. Or you can pack them properly and this way. But however, if you want to pass a record into a function, which has an open record in its data type, that basically means you don't know exactly where it is. In JavaScript, that's no issue because you can simply pass along the name, or you don't even have to, because you can derive the name from the type and then tell the JVM, because every the JavaScript engine, to pick me whatever is on this name. So if I say I want a record which has email on it, but I don't care about everything else, in JavaScript, you can simply say, give me email from this JavaScript object. That does not work with GHC because you compile it to machine. You prefer to have less pointers. However, if you say that here, pass me something with email, but I don't know where exactly it is, which means that you cannot statically at compile time determine where exactly on this data type is my data. So this means that open rows would have more indirection. I have no clue how expensive this would be. This is simply another issue to be thought about. Now, this is basically my very rough introduction into row types. I have 3 more minutes according to my talk length. However, I could talk more about how would you actually use row types, like with row to list, which gives you a type level list which you can iterate over. But I figured this would be a good starting point on introduction, why row types are actually useful, and a rough idea how they work.
Thank you very much, Simon. Does anybody have any questions for Simon at all? Is there any other things that you'd kind of like to ask or find out a little bit more? If you do, just use the Q&A section. Okay, if we haven't got any more questions at the moment, then feel free throughout the next talk, if you think of any, just put them in there and just put that they're for Simon, and we can make sure and ask them at the end for you all. Thank you very much for your talk, Simon.
It was a pleasure.
Thank you, Simon.
And we're now going to jump into Michael's talk, what makes Haskell unique.
Cool. Am I doing this with or without video? I think we should.
We can't see you. You can only see your screen at the moment.
Okay.
Oh no, you can see. Oh, we can see you now. We can see you.
Hi there. Okay. Cool. Thank you very much for having me today. Hi to everyone. I guess we've been hanging out for about half an hour already, so let's keep going with this. I'll tell you that normally at this point in this kind of a talk, I'd probably start asking around in the audience who here has experience with Haskell, who knows a little bit of functional programming, and then people would start raising their hands and I'd get a pretty good idea. We're not doing that today because, you know, I can't see you. So because of that, I'm going to make some assumptions and assume that most people on this call have a basic idea of what's going on in general with functional programming and know a little bit about Haskell, but not too much. I've got the chat window open. I will try to pay attention to the chat window as I'm going through this. Anyway, let's dive in. Okay. So the title of this talk is what makes Haskell unique? And then the first question is, why does that matter? Why do we care about a language being unique? There are lots of programming languages out there. I don't think anyone on this call is surprised to hear that. You have many options and you have to have some way of choosing amongst those options. We need some kind of a filtering mechanism for choosing languages. And the best one is to figure out what distinguishes one programming language from another. So the real topic of today is, if I'm going to use Haskell, what makes it special? And therefore, why would I care about wanting to use it? Probably the most prominent feature that people know about Haskell is that it is a functional programming language. You may also hear terms like purely functional or something else along those lines. So Haskell is a functional programming language. Great, that's why I should use it. Except that's not a great reason. Haskell is not the only functional programming language in the world. Scala, Lisp, ML, F#, those are all languages that at least claim to be functional and are probably considered functional in general. We don't even have a real definition for a functional programming language. One definition that I hear touted quite often is this lax definition that any language that has first-class functions and that has higher-order functions would be considered a functional programming language. Now that definition even C is a functional programming language, so the definition really begins to lose any kind of power. My point in all of this is, Haskell may be a functional programming language, but that in no way makes it unique. So I threw together this list of features of Haskell, adjectives perhaps, that people may apply to this language. It's functional and statically typed, it's pure and it's lazy. Strongly typed green threads, you can read. You probably see what I put up there. All of these things are features of Haskell. However, none of them are really unique. I can go through that list and I can give you examples of other languages that have each and every one of those features. So there really isn't any one feature that makes Haskell unique. There are in fact very few languages in the entire world that have no features shared with other languages. Go through the most popular languages you're aware of. Think about the top 3 things that you like about them, and you'll probably be able to find those 3 things in another language. Instead, I would say that we need to look at the feature stack of a language to understand the whole picture. In other words, it's not about any one of those many features that I mentioned of Haskell. It's about the combination. And Haskell essentially is unique in the world with that set of features. Most languages out there actually can make the same kind of claim. They do, each language has its own unique stack of features. Let's talk about how those features play together just a little bit. So one example is purity plus strong typing plus functional style. Not every, plenty of languages have strong typing. A number of languages have functional style, less have purity, but putting them all together really leads to a style of code that makes it easy to write, easy to read, easy to modify the programs once they already exist, and relatively efficient to run the code. And a lot of the talk is going to be touting some of those ideas. We're going to be diving through examples of how the various features that I mentioned before play together to give you this very nice experience, at least in my opinion, of the way Haskell works. For the most part, we're going to be talking about what makes Haskell different, what makes it unique, and therefore better. To try to be a little bit fair, even though I am obviously a biased person who loves Haskell, to try to be a little bit fair, I'm going to try to include some of the things about Haskell that are not so great, that are also unique. All right, so I'm going to start off with async IO and concurrency. So again, this is one of those, the audience can jump in. I'll watch the chat and see if anyone actually jumps in, but everyone's quiet so far. What's wrong with this little bit of code? I'm using pseudocode. I'm going to be using lots of pseudocode examples. So we're going ahead and we're calling HTTP GET. We're performing an HTTP request, putting the result into JSON, the variable JSON1. URL2 is going into JSON2, and then we're going to call another function, which is going to use these two JSON bodies. Well, the problem with it, at least in a simple view of looking at it, is that it's not actually doing things asynchronously. It's doing everything, at least in most languages that are out there today. Each one of those calls is going to block the entire system thread to perform these calls. So for people who are familiar with the way things work at the system call level, that essentially means you're going to have a system thread, a relatively expensive resource, sitting there waiting for IO to be performed on a socket, waiting for that to return, and many times doing the same thing. If you have lots of different programs on your system, or you have lots of different threads going on in your program, this is a very expensive way of approaching the problem. We like to be more efficient with resources, and that's why in many languages we have a callback approach, where we say instead of actually sitting there and waiting for the result to happen, we're instead going to ask for the HTTP request to be performed, and then we're going to continue with a continuation, a callback function. That callback function is going to be given the JSON body, and then I'm able to make the next request. And then afterwards, I'm able to combine together these two requests. This fixes the async problem that we had, because now if there are other threads in my, if there are other things that need to be done in my program, those things can get done on that same OS thread. We can share the OS thread, which is a more resource-friendly way of doing things. Unfortunately, writing code this way is not particularly pleasant. This is what's known as callback hell, and I'm sure some people on this call have experienced some level of callback hell themselves in the past. There are plenty of techniques in the world to work around that. Promises and futures is one. Async await syntax builds on top of that and makes it much more convenient. The question is, how does Haskell solve this? This is the asynchronous version of that code for Haskell. Now, besides the fact that we do things slightly differently with the syntax, we use that kind of bind-ish operator, the left arrow, and we don't use parentheses as much. This is exactly the same as the pseudocode I showed you before. The answer to, well, how can that possibly be asynchronous, is that Haskell, out of the box, ships with a green-threaded runtime. And therefore, when you make a call that looks like it's a blocking call, under the surface, the runtime system performs all the conversions necessary to turn it into an async call. It's going ahead and it's asking the OS to make the request. It's scheduling your thread to be started up again, your green thread to be started up again on an OS thread when data is available. And this is much more efficient with resources. But not only that, it's much easier to write this kind of code. Our brains tend to think much more in this kind of blocking, synchronous, direct way. We just want the computer to do it the more efficient way for it behind the scenes, and this is great. Haskell allows that to happen. Now, like I said, Haskell's not unique. Erlang and Go do something like this as well. They also have a green-threaded system. So if we really want to understand what makes Haskell unique here, we got to go deeper. There's also a problem. There's another problem that I didn't get to with that code example before. The way that we wrote the code up until now was nice to the operating system in the sense that it wasn't tying up an OS thread. However, I waited until the first URL was fully downloaded, the first request was complete, before starting the second request. If you have two requests going off to two completely different servers, that's actually very inefficient. We'd like to get both requests started at the same time, wait for both of them to complete, which hopefully is going to happen faster than doing things sequentially. This is standard concurrency. So the way that you would do this in most programming languages is you would start forking threads, you would have some kind of mutable variable, some kind of a mutex perhaps, you'd have to block, you'd have to do something to deal with locking, and you'd have to deal with exceptions that may get thrown or other kinds of error handling. Let's see the way that we do this in Haskell. That's the only change. We add this word concurrently. Concurrently is a library function from the async package. The async package is a wonderful package and captures a lot of really nice ideas about how to do concurrency in Haskell. Concurrently says, run these two things at the same time. Run them on two different green threads. It's very cheap in Haskell to spin up a green thread. Those two green threads get run. It waits for both of those green threads to complete. There's some cool business going on there about exception handling. People who are familiar with me know that I am a little obsessed with exception handling, so I'm not going to get into that right now. That's the way it works. And now we get, almost for free, with very little work, we get this concurrent, asynchronous, non-blocking version of our code in a way that's very easy to understand, read, and maintain. But let's say that we don't want to actually get both versions of those both requests. Let's say that we're querying two different servers that are serving the same data, and we only want to get, we want to just get whichever one comes back first and cancel the second one. Well, this is the way that you would do this typically with some kind of a promises setup. You'd create a mutex to handle the result. You would then set up two different callbacks. Each callback would have to manually cancel the other promise, and then you'd be able to collect the result. Let's see how it looks in Haskell. This looks almost identical to the way that we did things concurrently. Instead of the word concurrently, we use the word race. Race, like it sounds, lets two things run at the same time and waits for whichever one finishes first, and then it automatically cancels the other one. There's some niceness about the either type and the ability to pattern match in Haskell, but that's probably something you're already a little bit more familiar with. This depends quite a bit on asynchronous exceptions, which yet again is one of those almost unique in the Haskell ecosystem. Asynchronous exceptions are something built deep into the way that Haskell's runtime works. It has pluses, it has minuses, but here you're definitely seeing one of the pluses. Typically, in other languages where you have the ability to cancel some kind of an action, typically speaking, the ability to cancel comes down to I/O. You're able to stop some kind of something that's scheduled to start up when data is available on a socket, for example. In Haskell, you are able to go ahead and kill something which is even CPU bound. This is typically a problem. You can accidentally spin something that uses up CPU in a drastic way, and you're not able to kill that off in any kind of easy way. That's not the case in Haskell. You are able to use this exact same async exception mechanism since it's built so deep into the runtime itself. You're able to use that to kill off any kind of long-running CPU computation. So for example, if you have some kind of cache and you want to go check the cache and make an I/O call while you're still computing the value in the current application, you can do that. And you don't have to worry about that computation continuing to run afterwards. You can kill it off. All right, so summary of this point. Advantages in Haskell. You have cheap threads, these green threads. Very easy to spin up. You don't have to worry about the costs at the OS level. So there's a simple API to work with these things. You don't have to deal with mutexes. You don't have to deal with threads directly in many cases. It's highly responsive applications. The disadvantages of this, which I only very briefly touched on. There is a complicated runtime system that you're sitting on top of. It typically works very well and it works for most use cases and has the right behavior. But if you're in one of those weird cases where it's not going to fit the bill, you're kind of stuck. And async exceptions are something that I alluded to. They are a complicated topic and you do have to deal with them as a result of this being so deep in the ecosystem. All right, let's talk about another combination, immutability and purity. Most languages default to mutable values. Now, people on a call like this are probably more familiar already with languages out there that favor immutability. But still, the vast majority of languages that people are using allow variables by default to be mutated at any time. Haskell makes two changes to this. The first one is more common, and Haskell is immutable by default. That means that unless you have some explicit way, which I'll show you in a sec, some explicit way of saying that something is mutable, it is immutable and it can never be changed once it's created. The other thing that Haskell does, which is much more rare, is it treats mutating a value as an effect, and that effect is tracked in the type system. So let's see some examples. The first version of this code tries to add up the numbers 1 through 1,000,000 using a kind of for loop-ish approach in Haskell. The code is completely broken and it does not work. You're not able to go ahead and just add values to total. It's not allowed. Instead, the second version is the way that you could actually do this in Haskell. New IORef creates a mutable variable. This mutable variable can actually be changed. It can be changed using things like modify IORef. However, you'll notice that there's now this do sitting there in the middle. Inside Haskell, the only way that you can call modify IORef is inside IO. And by inside IO, that means that the type system is saying, this performs some input output, this has some effect on the outside world. We know that, and therefore we have to track it, and you have to keep track of it yourself and write your code just a little bit differently. Now, this is obviously not the way that you actually want to write code. We don't actually like dealing with mutability in this kind of a way. So the better way to write this in Haskell is to use recursion and be immutable, which is much better. So in this case, there are no mutable variables. Everything is immutable. That's the default. This code is much nicer, or at least I'm claiming it's nicer. Before I go a little bit further, I'm going to point out there is a massive bug on this slide. That is intentional. Everyone should take a second to think about it, look at it. I will be getting back to it later on. Okay, I think that's enough. So let's see why I care so much about mutability versus immutability. Again, we're going back to our pseudocode. We've got some kind of a CSV file, scores.txt, and it has the scores out for Alice, Bob, and Charlie on some test that they took for some reason that I don't know why. So they've taken their test, they've gotten their scores. I've written my main function. It's going to read the results from the file into some kind of a vector. Then I'm going to print out the results using this helper function, printScoreRange. And then I'm going to go ahead and print out the name of the first person whose result was handed in. Now, look at this code, take a guess. What would you expect would be the name of the first result? People can go into the chat if they want to, or you can just think to yourselves if you like to do that. Okay. When I look at this code, I would expect it to be Alice because, surprise, surprise, the first name in scores.txt is Alice. So that's the result I would expect. That's what I would hope for. Except we never talked about what printScoreRange does. Let's say that the way that it determines who got the lowest and who got the highest scores is by sorting that vector. It's going to be doing a mutable sort on a vector that was passed into it. That means that the main function's results are now going to be modified. No longer is Alice the first person in the vector. Now Charlie is the first person because he had the lowest score. Meaning a non-local change broke our predicted results. We made a change to a function, we didn't look at that function, and it mutated the variable that we were using ourselves, changed our expectations of what was going on. This is exactly the kind of bug that pops up all the time in mutable code. This is obviously a very simple example. Much more complex examples happen regularly. Let's see how we would do this in Haskell. In Haskell, this syntax change, fair enough. We read the results from the file. We pass in that results value to the printScoreRange function. Inside the printScoreRange function, we are taking in a list of test result values. We're not taking an immutable list. We're not taking in an IORef holding a list. Therefore, there is no way to modify the original value. The type system itself is guaranteeing it. If I tried in any way inside printScoreRange to change that value, the one in main, it would fail. So therefore, when I get this sort by function, I know that it's got to be modifying, or it's got to be creating a new value instead of modifying the existing one. And therefore, this function, this code is going to work correctly. What's really nice about this is I can look at just the type signature of printScoreRange, and I can know that that's what's going on based off of the type of the value that I'm passing in. That means that I don't have to go analyze a whole bunch of other code to understand what changes it might be making. I can just look at type signatures, keep my focus laser focused on that. Let's look at another example, data races. So I'm going to read results from a file, results.txt, And now concurrently, I'm going to print the first result, and I'm going to print the score range, the score range, print the lowest and the highest. Notice what's going on here. I have two different threads that are both concurrently accessing the data. This is typically the point at which you would start getting nervous in concurrent programming. I'm not getting nervous in this case though, because I know that I'm passing in an immutable data structure. I have no fear at all of the idea of multiple threads accessing my data, or at least reading my data. And the reason is I know that there's no possibility that they could write to the data. Now you might be wondering, yeah, but what happens when you actually need multiple threads to be able to mutate things? That does come up. We'll get to that later in another example. Here's a simpler problem though. What if you really, really need mutability for some other reason? A nice example would be you have an algorithm, like a sort algorithm, and that algorithm is going to be much faster if you work with a mutable data structure. Sorting a vector using immutable operations is much, much slower than, say, a standard insertion sort. So Haskell's answer to this is that you can still have mutable data structures. You just have to be explicit about them. And then when it comes to these kinds of operations, we have a technique of doing a temporary mutable copy, doing whatever kind of modifications we need to it, and then freezing the data structure. Let's see what I mean. Let's say that I have a mutable vector data type. This thing actually exists. It's called something slightly different, I think M vector. But let's say that I've got a mutable vector data type. And then I go ahead and I write a function that is going to perform some kind of nice, fast, standard, textbook sort algorithm on it. But I don't want to deal with mutable vectors all throughout my code. I want to live in the nice, pure world of immutable vectors. So I want to write an immutable sort based on that. The way that I do that is I start everything off with run st. St is what's called the strict state transformer. And what it's doing is it's creating this contained world where I'm allowed to make mutations. Inside this world, I'm not allowed to mutate variables from outside, and variables from the and nothing from the outside of this world are able to look at the mutations I'm making to stuff inside. So it's kind of like a temporary world where I don't need to worry about any kind of impact on anything else. This is a great way to get mutability, but at the same time, get all the guarantees of purity that I want. Purity meaning I'm going to have a function, and given the same input, the output will always be the same. So once I'm inside run st, I'm going to use a function immutable vector. I'm going to create a mutable vector of the same size as the original vector. I'm going to copy the values from the original vector into the mutable one. Then I'm going to call that exact same sort mutable and get the nice efficient sorting that I've already written elsewhere. And then I call freeze on this in order to create an immutable vector. This is the way that code actually works in the real world. In fact, this is longer than the real version of a sort function that I've written. There are helper functions that hide away all of the copy and the new vector and the freeze. All that stuff is actually handled by something called modify, and it just works that way. I wrote the longer version so it was less magical what was going on. But this is a real way that you can approach things. You can get the benefits of fast mutable algorithms, but at the same time keep the sanity of immutability. All right, so the summary of immutability and purity. Advantages. It's much easier to predict code behavior. You're able to avoid many cases of data races. Not all of them. You can still have data race issues, but the number of cases goes down dramatically. And as a result of all this, functions are far more reliable, and you get the same output for the same input when you have these kinds of pure functions. Disadvantages. If you actually want to work with mutation, there is a lot more ceremony that you have to do in Haskell than you would in a language like C or Python, which is mutable by default. And when you actually want to use mutability, there is going to be some kind of a runtime performance hit for those copies that you're going to be making. By the way, no one's asked any questions. Feel free to pop some questions up if you have them. I'm going to keep going because weird, awkward silences are always fun. But if you have questions, go ahead and pop them up. Happy to answer them. All right, concurrent mutation. Have a good look at this code and try to tell me what is wrong with it. The idea is that I'm running some kind of a server. The server is keeping track of bank accounts. And the bank accounts and the server is allowing requests to come in to transfer money from one account to another account. The code looks reasonable at first. However, when you actually pay attention to what's going on, you can see we're first reading the value of the from account, reading the value of the to account, then writing to the from account and writing to the to account. That also might seem fine, but once you start looking at a possible way that two threads could end up working on this, the problem pops up. So let's imagine we've got thread 1 and thread 2. Thread 1 receives a request that Alice wants to give somebody $10. Thread 2 gets a request that Alice is going to receive $10 from somebody else. Thread 1 and thread 2 both look up Alice's account balance at the same time, and they both see $50. So thread 1 is now going to see that $50, subtract $10 from it, and set that as the new account balance. Thread 2 knows nothing about the $10 that was just taken away, knows nothing about the $40. It still sees $50. So it does 50 plus 10, writes that to the account. Poof, money has been created out of thin air, which actually, given the fact that I'm using dollars and talking about Americans, that actually might be a reasonable hypothesis of what goes on. That said, that's not the way we actually want our code to work. In a typical kind of imperative world, the standard way that you would approach this is by some kind of locking. And you would say, I'm going to lock the first account, the account that things are coming from. I'm going to lock the account that money is going to. Now I know for a fact that nobody else is going to be modifying these two variables. I'm going to do all the reading and writing that I did previously. That's fine. And then I'm going to unlock these variables. Problem is, yet again, imagine that you have thread 1 and thread 2. Thread 1 wants to send money from Alice to Bob, while thread 2 wants to send money from Bob to Alice. Thread 1 locks Alice's account because that's its from. Thread 2 locks Bob's account because that's its from. Thread 1 then tries to lock Bob, but it can't do that because thread 2 has already locked it. So it sits there and waits. And thread 2 tries to lock Alice, but it can't because thread 1 already has it locked. So it blocks and it waits. This is what is known as a deadlock. Neither one of these threads is able to make any kind of progress. They're both stuck indefinitely until someone basically kills the process. So how exactly would we solve this in Haskell? Well, this code looks very similar to what we saw previously. The only two differences really are I've rewritten it into Haskell syntax and I've added this word atomically, which I haven't really explained yet. This looks like it has the exact same race condition. We're reading the variables and then we're writing and we're not doing any kind of locking at all. However, that atomically word is very important. STM, by the way, STM happens to be one of my favorite things in Haskell and one of the things that I think is one of the best demonstrations of the power of Haskell. What STM is doing here is it keeps a transaction log. It notices which variables, which tvars, transactional variables, it has looked at previously. When it tries to commit this transaction, when it finishes that atomically block, it goes in and checks if any of those variables have changed since the last time it ran. Since it started running the transaction. If any of those variables change their values, then all of the work that it did is wiped away and it starts over, it retries. And that way, you don't actually have to write any kind of locking code. You don't have to worry about what other threads are doing. If your changes commit, that means that you saw a holistic atomic view of the world and everything just works. This is a massive simplification for the way that we write code in general. So let's see how purity comes into play, because purity is something that I talked about before. Let's say I'm writing an application which is going to buy Bitcoins and keep track of how many Bitcoins I'm going to use. I've got this function, buy Bitcoins, and it transfers money from my bank account to some shady person out in the world who's selling me some Bitcoins. Let's say I've got this modify tvar, my Bitcoin count. Now, based on what I just told you about retries, if some other thread modifies this variable at the same time, it's possible that my transaction is going to get restarted. That seems like it would be a very big deal. Buy Bitcoin is actually going to affect the outside world, and it's going to transfer thousands of dollars each time it gets called into somebody else's bank account. This could very quickly wipe out my bank account. So I'm not happy with this code. How do I prevent that kind of a problem? Well, it's actually completely a trick question. The code you're looking at does not compile. Buy Bitcoin has effects on the outside world. What I told you before, about effects getting tracked at the type system, Buy Bitcoin performs I/O. So it says that it does I/O. You're not allowed to perform I/O inside of an atomically. And therefore, this code won't compile, and you don't have to worry about the possibility of Buy Bitcoins getting called multiple times. In other words, the reason why the runtime is able to do this whole retry trick is because of the impact of purity on the language. So we're seeing one of those combinations. STM together with purity gives a value that neither one of those features on their own would have given. So, summary of STM. Advantages: it makes concurrent data modification much easier than the alternatives. You get to automatically bypass many race conditions and deadlocks. I keep giving this kind of a caveat. It is still entirely possible to have a race condition or to have a deadlock in Haskell. Haskell is not a panacea that solves all problems. All it's doing is reducing the likelihood of that happening. Disadvantages: STM really only works in the context of purity. You can technically implement STM, you just have to be very careful in a language that doesn't have purity. You have to pay the cost of purity, which really, if you're already in Haskell, it's a cost, it's a sunk cost. You don't have to worry about that when you start moving over to STM. So if you're in Haskell, if you're using it, I definitely recommend read up on STM. I have a talk available, a workshop, in fact, on STM. If anyone's interested, I can find the link and send it later. Okay. Laziness, a double-edged sword. So you can see where this is going. I told you much earlier that there was a massive bug in this program sitting in front of you. So go ahead and have a look at it again. There are two problems with it. One is that performance bug, and the second, this is really cumbersome. It is very difficult for me, and I've been staring at Haskell code for many, many years. It's difficult for me to look at that and immediately know what it's trying to do. So I don't like that. And worse, the fact that it's so cumbersome is really what's hiding away the performance bug. Well, anyway, let's figure out what that bug is. Space leaks. Haskell is a lazy language. So when you have something like let foo equals 1 plus 2, in most other languages on the planet, that means foo now holds the value of 3. In Haskell, that's not what it means at all. It means that foo is an instruction on how to create the value 3. This is actually known as a thunk. The thunk is holding this recipe, and it's holding a pointer to the plus operator, and a pointer to the number 1, and a pointer to the number 2. When that thunk gets evaluated, in other words, when the value is actually needed, at that point, it's going to go off and figure out what 1 plus 2 is. And that's why this is called laziness, because Haskell is being very lazy. Now, as a side point, in a simple example like this, odds are the compiler is going to see through this and realize, yeah, it's really, really cheap to figure out 1 plus 2, and it's going to do it for you. But we're going to pretend like the compiler is incredibly dumb. And in that case, foo is going to hold on to this plus this thunk, this plus the 1 and the 2. Now you can imagine it is much cheaper for a computer to hold on to a single integer than it is to hold on to that entire formula that I just told you of how to construct 3. All right, now that I've given you that preamble, let's look at our little code, our little example again. Which values are evaluated each time we go through loop? Well, we've got two different variables coming into loop. We've got I and we've got total. I is being compared against the number 1 million. And therefore, it's actually going to be evaluated. You can't compare I to 1 million without knowing what I is. So I is actually going to be evaluated each time. So if you look a few lines later, it says loop of I plus 1. That I plus 1 is going to be evaluated. It's not going to create a thunk. It's not going to create a space leak. However, the total is never evaluated. Nothing here requires knowledge of what total is equal to. And therefore, when you do total plus I, it's not going to actually add these two numbers together. Instead, it's going to create a thunk. And when you do this, what you're actually doing is you're creating this tree of 1 million thunks that ultimately can be reduced. Holding on to all of that uses up a whole bunch of memory. It is far less efficient from a CPU standpoint. It's bad in every way you can imagine. So this is just horrible code. If you're lucky, GHC may optimize this, it may not optimize this. So how do you solve this kind of a problem in Haskell? The answer is with strictness annotations, or the bang pattern. So here you can see I put an exclamation point, also known as the bang, in front of the variable total, the parameter total. What that's saying is each time the function loop gets called, make sure that you evaluate the value total. This solves the problem that I was just mentioning. This is a huge downside. The fact that I have to write this sucks. It is annoying. I don't like this. No one likes having to write the code like this. I have an escape route for when laziness shoots me in the foot, but this just begs the question, do I get any kind of benefit out of laziness that makes it worth sticking up with all of this pain? Let's take a little bit of a detour for the moment and talk about looping. Let's say that we've got a standard kind of imperative language with for loops. This is the way that we would probably add up the numbers 1 to 1,000,000. We'd start off with a variable, it would be mutable. We would then write our for loop that says we're going to have I go from 1 to 1,000,000, and then we would add to total each time. Basically, any programmer who's ever learned a C-style language can look at this and understand more or less what's going on there. Now let's say that I want to modify this just a bit. I only want to add up the even numbers. I don't want to add up all the numbers. Well, that's not too bad. I can put if is even inside and conditionally do the mutation on total. Well, now let's say I want to add up all the numbers, but I want to do it modulus 13 for some god-awful reason I can't imagine. So I've gone ahead and I've done that. And I keep modifying things deep inside my for loop. Each of these modifications is fine. There's nothing particularly complicated about it, but it really does start becoming difficult to see what's going on. You start losing the forest for the trees of all of this. And here we're talking about some really simple examples. The number is 1 to 1,000,000. If it's even, modulus 13, add it up. I can say it very, very directly. I could write it down very directly in English, but this code kind of hides away what we're doing. All right, now we get to go back to Haskell. I told you I did not like the recursive implementation of this loop. It was cumbersome, and I hated having to deal with the bang pattern. Here's the way that you actually implement this in Haskell. You use a fold. Oh, it's supposed to say fold L, sorry, I mistyped that. So you go ahead and you have a fold, which is going to fold the addition operator, starting with 0 over all of the values in the list. So folds now are, folds or reductions are now a fairly common concept in many other programming languages. They are essentially the basis of how functional programming is supposed to work. It is much nicer to be able to look at this kind of code than it is to have to write that explicit recursion all over the place. Someone coming from a strict language should be asking me the question, that list of 1,000,000 numbers, that should take up about 8 megabytes in memory. Why doesn't it? Well, the answer is laziness. We don't actually generate that list all at once. Instead, we have a list which is currently a thunk. And as the fold starts going through it, the thunk gets evaluated just a little bit more. We get the next value out of the list, and the rest of the list becomes a thunk. And we keep going through that. We keep throwing away the garbage, taking the next one, adding things up. The strict left fold handles all those laziness issues I mentioned before. And we get a constant space implementation of sum. And in fact, there is a function called sum, which I'm going to use for the rest of the slides, that does all this for you out of the box. So here we're starting to see the benefits of laziness. We saw the costs first. Now let's compare this against making more complicated versions that we saw in the for loop version before. If I want to do just the evens, I'm able to just filter for evens. The fact that lists are lazy means that this works. You could write code like this in, say, Python, but if you do it in Python, you're going to most likely end up with multiple copies of the array allocated in memory, not so in Haskell. And then doing everything modulus 13 is simply a matter of mapping a function over the results of the filter. It's easy and it's natural to compose functions when you have this kind of lazy approach to things. It's much easier for us to look at this code and at least for me, I find this much easier to look at and understand than the for loop approach. Another nice, nifty little advantage. Almost every programming language has short circuiting, and that applies typically to the and or operators. And in C, in C++, in Java, if you do foo and bar, foo is going to be called, and then if it returns true, bar is going to be called. If foo returns false, bar is never actually going to be called. And this works great in most other programming languages, but it had to be built into the language, and these operators kind of don't fit in with everything else. They're an exception to all the rules. That's not the case in Haskell. You can actually go ahead and write your own lazy function, lazy operator yourself. And that's the implementation right there in front of you. If I remember correctly, that's the actual implementation in the base library for Haskell itself. And you can see from the fact that the first pattern match for and uses a wildcard pattern, the underscore, for when the first case is false. You can see it doesn't care what's going on in the second argument when the first argument is false. And the reverse goes on with or. There are other downsides that come along with laziness. The biggest one, and the one that annoys me the most, is the fact that you can have exceptions hiding in any thunk. Now, this isn't too terribly different than the way things work with function calls in most languages, where you can have an exception explode in your face when you make a function call. However, it irks just a little bit more in Haskell. When you have a value that says it's an int, you really expect that you already have that int. And you now need to take into account, well, it might be an int. It might be a computation which will generate an int. It might be a computation which, when I run it, is going to cause a runtime exception to be thrown. Going along with that, Haskell has too many partial functions. I recommend using replacement preludes, meaning libraries that come out of the box with these partial functions hidden away, because you shouldn't be using them. We almost always have better approaches. So head, for example, is a function that gets the first thing out of a list. It's nonsensical on an empty list. Instead, there are functions like head maybe, which would say, hey, go ahead, try to get the first thing from the list. If it's there, return it. Otherwise, return a nothing. And this is an option type in Haskell, and that's the way that I would recommend it. Go ahead and let the type system tell you what your code may be doing. The other big downside, and this really annoys me, is the fact that inefficient functions are available. You notice that I used fold prime. I put that tick at the end of it. That means be strict. When it comes to fold L, you always want the strict version. There are almost zero cases ever in recorded history where the lazy version is something anyone wanted. And yet that's the one that's available by default. So this is yet another argument for, if you're going to use Haskell, make sure you use a good prelude that avoids some of these kinds of paper cuts. So, summary of laziness. On the advantages side, you get more composable code, you get efficient results with high-level code. You don't have to go down to the level of, you don't have to go down to the level of writing for loops and throwing everything together. You can just write a nice long composition and get efficient results. And short-circuiting just comes for free with the way that laziness works. Disadvantages: you need to worry about space leaks, exceptions can hide in more places, and bad functions like lazy fold L and like head still exist in the language. Just as a side note, other languages have some of these advantages of laziness as well. So for example, in Python, you've got generators, or Rust has iterators. And I've actually written quite a few blog posts on Rust's iterators and how they play in. Many of the approaches that I mentioned to writing code with Haskell's laziness can apply in those kinds of cases as well. One of the things that I would recommend is, if you're using one of those languages and you have those tools available and you want to get more comfortable using them, use a language like Haskell for a bit. Learn how laziness works. It'll be much easier after that to go back to that other language and use those tools the right way. So I think I said that this was going to be a 40-minute talk. I think I'm coming up on that. I definitely expected to be coming up on that at this point. I was going to mention one or two other topics. I may have taken out the second one. I don't remember. We're about to find out together. Something that Haskell is often used for is parsers and other DSLs. Why is Haskell such a good language for these kinds of DSLs, this domain-specific language? One of the big ones is operator overloading. You are able to create basically any kind of operator that you want in Haskell. Now this can be abused, and it oftentimes is abused. I'm not a fan of some of the craziest examples, But when you're really dealing with a specific subset of functionality that you want to be working with, having the ability to define your own operators is great. Another thing, we have many abstractions, like the alternative type class. Alternative defines the ability to say, hey, I've got this or I've got that, and take whichever one works. And that seems pretty vague. And the nice thing about it being vague is it actually applies in many different cases. So in the case of a parser, you could say, I want to parse an XML element. But if that fails, if it's not an XML element, I want you to try to parse XML text. And then it's going to return whichever one of those completes first. This also works for concurrency. That race that I told you about before, you can use the alternative operator to say, hey, I want to run this or I want to run this. Just give me whichever thing completes first. Since we put things like the alternative type class deep at the core of Haskell, and we encourage people to write their code in terms of it, you out of the box get a whole bunch of different combinators, helper functions that you're able to use. So for example, optional. Optional can be used with parser combinators to say, hey, maybe I'm going to see a comma here, or maybe not. Or you could use it for command line option parsing to say, hey, this is an optional flag that doesn't need to be present. You can also use many to say, hey, I want to parse many different XML elements in a row, or other things like that. In addition to things like the alternative type class, we have the traversable type class with traverse. I know many Scala developers are big fans of traverse, fold map, et cetera, et cetera. So having this common set of concepts, of idioms, and having everything built on top of it means you don't have to learn a new library, a new set of functions each time you jump over to some new domain. A lot of your knowledge persists. Also, the fact that Haskell has do notation really means that you're able to define whatever kind of language you want to be working with inside each specific example of do notation. Just as an example, this is a way that you would end up writing a time parser in Haskell. And you can see we've got these operators, the $ inside angle brackets. This all comes from the applicative type class. And applicative is like a dumbed down, a weakened form of monad. And it allows us to write these things pretty easily. So we're able to say, hey, parse out the number. Then I want you to parse out the colon, and then parse out another number, parse out another colon and another number for the seconds. And then optionally at the end, I may have AM or PM. So go ahead and try to parse that if it's there. The final topic that I was going to mention is advanced techniques. Advanced techniques exist all over the place in Haskell. Free monads, monad transformer stacks. I probably should have put, shoot, what is it that I wanted to put in here? Anyway, there's a whole bunch of these things. There are always a million different ways that you can do things in Haskell. This is a plus and a minus. You always have another approach if the one that you're using fails you. You can always have something new to learn. My very, very strong recommendation is to withstand the temptation to make your Haskell code too complicated. This is the kind of thing that pops up a lot in production Haskell code. Haskell is a lot of fun, and you get a lot of opportunities to play around with concepts that you don't really get to play with in many other languages. But if you're actually writing code to be useful, write code to be useful. Leave the brain bending stuff to later. And if you're familiar with it, I've written some blog posts on the topic around writing boring Haskell code. All right, so conclusion. Haskell combines lots of uncommon features. None of those specific features are unique, but they are less commonly used. In fact, I said very few of those features are unique. None of them are really unique. They exist everywhere. And every one of them exists in another programming language. However, combining these features allows you to write code in Haskell, which you would never really write in other programming languages. In my opinion, you get very readable, very robust, easy to maintain code, and I'm a very big fan of it, and I think it's definitely something worth taking a look at. And on the other hand, just be aware there are sharp edges. Like any language, it's not perfect. There are plenty of issues. You should be aware of those as you dive in. Okay, and that is the end. So I've yet to see any questions pop up or any chat messages. So this is a very quiet audience, even by remote standards.
Thank you very much, Michael. Yeah, if anybody's got any questions, I'll put back on. If anybody's got any questions, make sure you ask in the Q&A section. Oh, perfect. I have someone said it was really good. So well done, Michael. Thank you very much. Oh, there you go. There you go. We've got some thanks coming in now as well then. Perfect. No, that was really great from both you and Simon. So a massive thank you for you both to kind of like taking out your time to give us some more insight into Haskell. Hopefully going forward, we're going to have some more like Haskell meetups. You've obviously all been answering the poll as well. And so it'll be interesting to see what you say. But massive thank you to everybody for jumping on this afternoon. Well, like I said, we're going to have lots more. And if there's any kind of like any subjects in particular you'd like to request, we just had a little question on the chat section.
Sure. Shall I dive into some of the questions?
Go ahead. Yeah. Oh, there's some more questions going on, so just answer the questions and just.
Sure. Okay. So, what prelude replacement would I recommend? I've been working on one called Rio for the past few years. Working on for a few years is probably a misstatement. I've been using it for a few years. I worked on it a few years ago. That's the one that I would recommend. I've tried to balance out some of the common things that people want to be able to do without going crazy. And it recommends a set of standard libraries, a set of extensions, and a set of best practices while hiding away some of the rough edges. That's the one that I use in almost all of my projects these days. I've been moving more and more of my libraries over to it. That's how I would approach it. Let's see. What is the killer app for Haskell? I think concurrent services is probably the biggest example. The other big one, Haskell is huge in the finance sector, and for good reason. Haskell has the ability to be more easily correct, faster to make changes to the code, and get good performance. Those kinds of things matter a lot in sectors like finance. We've used it in the life sciences space, where you have, when you make a mistake, you either lose a whole bunch of money or someone dies. That's a really good place for using Haskell. That would be some of my recommendations. Let's see. Just going through some more of the questions. Can Haskell be classed as an object-oriented language? I'm not sure and I don't mean this to be, I'm not trying to be flippant. I'm actually not quite sure what object-oriented means in general. I would say probably no, Haskell isn't an object-oriented language. But again, so many of these definitions get thrown all over the place. The one that peeves me the most is when people call XSLT a functional programming language because it's declarative. Well, yeah, but it doesn't even have functions. So you could say the same kind of thing about Haskell. Is Haskell object-oriented? Well, what's an object? It does have the ability to have values that you can pass messages to. Is C++ even object-oriented? It doesn't really have proper messages the way object-oriented programs were supposed to in the first place. So if someone was really, gun to my head, is Haskell object-oriented? My answer would probably be no, but I guess you could theoretically make an argument in that direction. I'm not sure if that was too vague an answer for you or not.
I may add a tiny bit on top of that. There is a thing called the service pattern, which is, I think, is kind of similar to object or some style of object-oriented programming, but because it's basically a pattern, that means it's not built into the language, which basically lends same argument. It's probably not.
It could be. I'm not sure. I could go both ways. Okay, next question is, what is the current direction of the Haskell world? So Haskell's always been of two minds. There are basically two different strands of direction that it's always going down. There's the research side, which is really pushing the bounds of what we're able to do with type systems, what we're able to do at a language implementation level, even things at a very pragmatic level like STM. Those were cutting edge in the Haskell world. Some of those things turn out to be amazing for industry, and that's why Haskell's been able to do some really great stuff. Some of them turn out, in my opinion at least, to be less valuable to industry and things that I don't necessarily follow as much. So at the same time that you have this research bent, which is pushing the bounds of things, you have the industrial side of things, which is saying, yeah, I kind of like that thing you're doing, but I'm not so interested in that other thing. And I definitely come from the industrial side, not the research side. And on the industrial side, we're basically saying, yeah, we like Haskell the way it is. Let's make it a little bit faster. Let's improve the library ecosystem. Let's improve documentation. Let's get tooling to be a little bit better. And those are the two different directions right now, as far as I see it. Simon, feel free to jump in. I don't mean to hog all the answers.
I think we've got one more question on the Q&A section.
Yeah. So why is it so hard? Why is it hard to get a Haskell job if it's such an awesome language? Believe it or not, the talk I'm giving next week at LambdaConf Online is all about that. It's about if Haskell is, let's say that I'm right. Let's say Haskell is the greatest language on earth, and everything written in Haskell is golden and beautiful. Why isn't every single company in the world using it today? You could make the same, basically every single person who advocates any language probably asks themselves that exact same question. And there are some basic answers like, well, Haskell isn't perfect for every single application. There are things like real-time applications where you need something like C++ or Rust. There are other kinds of domains where, Python with SciPy is leaps and bounds ahead usability-wise than basically any other language on the planet. So there are definitely those kinds of subsets, but generally speaking, why isn't Haskell edging out a language like Go or something? It's a great question. There are many factors, and I don't think all of them are technical. There are definitely some technical things that we could be doing. Improving compile times would be an example. But in many cases, the reason why Haskell isn't really taking off is because there's some kind of social or economic is actually the one I'm going to talk about next week, aspect to this, where it's saying, yeah, people are making a decision based off of non-technical reasons or based off of assumptions or something else that makes Haskell look like a bad fit for this kind of a use case. One of them, in my opinion, is the fact that Haskellers tend to write code which is just a little bit too complex in general. And that causes some trouble, some reputation issues. It's not inherent to Haskell, but it is something that we have to deal with. Okay. Oh, can I send the link of the talk you'll be giving? Yes, I think I can. I don't know. I actually don't know where the information is for LambdaConf. If you're following me on Twitter, I will definitely find a way to get that out there. I'll see if I can find it here and put it in the chat. Simon, did you want to take one of the questions?
So I was currently on the JavaScript basically looking up something for space leaks explicitly. I had the exact issue with a space leak a few years past, and my solution back then was basically to hit up the some small consultancy. They call themselves Dirty Cheap Haskell consultancy, and they basically just wrote me a nice little write-up on how exactly you find space leaks. So that's what I'm currently trying to find. They gave a really good write-up on it.
Sorry, you did by Nissan. Oh, as far as tools, there's a built-in heap allocation heap tool, and the built-in RTS-S option will look at runtime statistics, and you can get a very good idea of things there as well. One of my coworkers, Chris Dunn, wrote a tool called Way, a library called Way, which is basically automated testing for space leaks or for space usage in general. So those are some of the things you could use. And I'm putting in a link to the conference that I was just mentioning into the chat.
There's another question there in the chat. So I've got one more. We've got another one here from Paul in the Q&A. We've got one in the chat as well from Joe.
Sure. General recommendations, when to use state versus ST. Yeah, use state if you can, basically. If you have something going on that needs the additional performance that can be gotten from mutability, then use ST. I can tell you in practice, I almost never use ST in my code. Usually, if ST is something that I would need, it's something that a library has already been providing. It's something that pops up very rarely. So that sort example that I gave you. Hopefully, you're not writing the sort function yourself. Hopefully, someone else at a library level has written a function for sorting immutable vectors. It's not the kind of thing an application author should be doing. It's a library author job. And hopefully that's provided. So I would typically recommend, if you don't know that you need ST, odds are you don't need ST. Okay. Joe, what can we do about the Haskell community feeling a bit highbrow? I think we need a lot more blog posts, talks, and other things along those lines, talking at a basic level. We just need to get out there and say, hey, look, I had this problem where I was talking to a JSON API and I wrote a solution in Haskell and this is it. Sometimes it feels intimidating to go to the Haskell community and say, I wrote a boring application and it worked. those are the stories we need. We need a lot more of those. We need less, yeah, well, I wrote a compiler for this new language in Haskell, and I wrote an optimizer, and then I was able to use the traversable instance. No, we don't need that. Show us that you actually wrote something. I have a website, and the website is up. I want to see those blog posts. I will reshare those blog posts any chance I get. Promise.
And you've shared that link, haven't you, Simon, for the space link in the chat section?
Yeah, I found the story in the Space League. It's a pretty good write-up, and I can recommend going through it, and it will teach you quite a bit about it.
Amazing, perfect. So do we have any more questions? There was quite a lot of questions at once, wasn't it? Perfect. No, well good. Amazing. Well, thank you so much, guys. As I mentioned, we'll make sure and put this recording up, so anybody that wants to kind of catch up on anything, you can do that. And again, any requests you've got for anything specific, any talks, as you kind of mentioned with the Haskell community, if there's anything that us at Signify Technology can help with, definitely let us know. We're kind of all about helping whoever we can, to whatever's best for you. Perfect. Well, it was great to have you both on. So thank you much, Simon and Michael. And I'm sure we'll kind of have some more meetups coming soon.
Thank you very much. Thank you for arranging this. And thank you everyone in the audience. This was great.
Thanks guys for watching. Thank you.
Thanks for the setup.
Thanks.
Have a nice day, everybody.
Bye.